Yeah. All right. Good morning, everyone. It looks like the conference dinner decimated our ranks a little bit.
Yeah.
Okay. Well, I'm glad to see the survivors. I'm very happy to introduce Pierre-EmmanuelJabin for our to start our morning session, and he will speak on the mean field limit of non-exchangeable integrate.
Yes, but that's a fake title. I will give you the real one in 2 minutes. All right. So first off, I have to start with an anecdote of how I met Alexis, right, the first time. And it was at the beginning of my PhD. So like every one of us at that point, you were assigned a desk somewhere where you can work, right? So I show up to a room one day, and then this is a rough picture of what it looks like, right? So it's more or less what you would imagine. You have a big rectangular room, and then you have several desks facing the wall, right?
Yeah.
Except one. There was one desk at the end of the room, right? Was facing all the other desks. So everyone was, watching the wall, trying to work very, very hard. And then at the end, you have the boss watching everybody, right? And that was the boss desk. And of course, who was the boss? Was Alexis. So that's how.
There was someone before, right? When I came, I don't think I get to.
Yeah, this is a position that, of course, you grow into as you become more senior, right? But anyway, so that's the first time we met, and we've been friends ever since.
There is a messy desk.
Yes, that's Nader's desk.
Yeah.
Yes.
On your time, then.
Yeah, in your time as well. There was a desk with a huge pile of everything, and then Nader would only show during at night.
Yeah, we're on a different schedule.
That's why there's no one at the desk, right, during the day. And if you're wondering where I was sitting, well, the first year I was not allowed to sit in the main room. There was a small antechamber here, and I had a desk there.
But you took over right after.
I took over the boss desk after Alexis, yes. All right. So let me switch a little bit to math, but only half. Don't worry. So I'm not directly going to talk about something that has to do with fluids, and I felt a little bad about that for a while, and then was tempted to change the title. But then I found a bad joke to go with the talk, and I thought, okay, now I have to stick with it. So here's the real title of this talk, which is trying to understand Alexis' brain.
Just open.
Yeah, that's usually a one-way understanding, so it's not very useful if you want to do anything with it afterwards. So let's try the math way, right? So it's actually a very long tradition of trying to model the brain activity. And it's among the first biology models that we are derived from that. And I'm going to show you one example, which are called integrate and fire models. And the way you do integrate and fire, so we are going to take a certain number of neurons, right? And I'll give you some scalings in a minute. And we are going to track the membrane potential of each neuron, okay? So let me denote VI, which is this membrane potential. right? And I goes from 1 to n, so let's number the neurons. For the moment, choose any numbering you want, right? From 1 to n. And we are going to do the following thing. Neurons will have jumps, right? The membrane potential will have jumps. This is what we call the firing of the neuron. Let's ignore the firing for a minute. In between the firing, each neuron follows a very simple equation, which is a closed SD, right? So ddi equal b of vi dt. And let me put a 2 here so that I don't have to put it anywhere else. dwi. And the wi's are independent Brownian motion. Okay. So what this does, of course, is if you look at a neuron potential, right, it's going to be slowly growing, but with a lot of noise. And then a neuron may fire. And the firing in that model is a random event. So it's a Poisson process, to use sophisticated words, right? With a certain rate that depends on the membrane potential. So the higher the potential, the more likely the neuron is to fire. All right, and I'm going to denote mu of v, the rate of firing. What happens when a neuron fires is very simple. You put back its potential to 0. Now, in reality, there's a rest potential in the brain, and it's not 0, it's slightly negative, but we can just, shift everything so that it's at 0. All right? So then, if you have a fire of a neuron, immediately after the firing rate, so I'm going to denote, if you fire at time t, I'm going to denote that time t plus, right? You are at 0. Simple enough. There's not a lot, so that should be okay. What's interesting and what makes the dynamics worth studying is what happens to the other neurons when one neuron is firing. For all other neurons that are connected to the neuron I, then there is a small jump in their potential. Right, so VJT plus is VJT minus, so just before the firing, plus something that I'm going to call WJI. And this is a map of connections between neurons, right? So this matrix of weights tell you which neuron is connected to which and how strong the connection is. And this is the whole point, right? So this is what is going to create all the problems and all the fun and what I'm going to say afterwards. Now, just a few words on this model, and then I'll start talking about scaling, and I'll start talking about what we can do to study limits of that for a very large number of neurons, right? The first version of that, without connection between neurons, but this, right, and was due to Le Pic and its beginning of the 20th century. To give an idea of how old this is. And this really took off after World War II, and you have a huge amount of literature that I'm not going to try to cite, slowly building on this. You have tons of variants of how you can write things. So for example, you'll notice here that my potential can be negative, because the Brownian motion, right, is a Brownian motion. It can go both ways. So it's not very likely, but it will happen from once in a while. You could, of course, try to put a boundary condition at 0 and have a reflected Brownian motion or something like that, right? You can remove the Brownian motion here. This is especially common because we already have some randomness in when the neuron fires, right? Or you can say that the neuron is going to fire at a deterministic threshold. And so you have tons of various ways of writing those models. Some of those ways are very transparent for what I'm going to say, and others I don't know how to do it. A different set of models here are what I call Hawk's process. And there's a huge probabilistic literature on that. Eva Loscherbach, in particular, has a great review paper for that you can check. And of course, you can also say, yeah, but you know, I remember different models for neurons where you had very complicated stuff like Fitsug-Nagumo and then things like that. And so I'm not an expert in the modeling of that. What I'm being repeatedly told is that those more complicated models actually don't perform that well when you put them all together in a network. So this sort of simplified model where you have a well-identified jump seems to be considered as more accurate when you're looking at network of neurons. And I'm being careful here because, again, that's not my... A last word about this, which is you might wonder, is it simple to show well-posedness of a model like that? And the answer is not quite. There can be a few problems with the interaction here, right? And in particular, you could, in principle, have a blow-up in that model where all neurons start firing all at once, all the time.
And that explains his brain?
Yeah, I was going to make a joke about this, right? That sometimes you see Alexis freeze and he's thinking very, very hard, and then that's the... but there are reasonable conditions on all the functions that I put here that can avoid that. There's a paper by Delarieux, Inglis, Rubenthaler, and Tenré, which is doing this. So I'm just going to be a bit fuzzy here and say, yes, I'm going to take nice functions so that I don't have this kind of phenomena. And then this is well posed, and I have existence at least to my starting model. So the next thing I want to discuss a little bit is the scaling. So first, how many neurons are we talking about? That depends a little bit what you want to look at, right? Do you want to look at the whole brain? Do you want to look at only the math piece of Alexis' brain? The numbers, of course, will change, right? But the human brain is around 10 to the 11 neurons, right? That's order of magnitude. The most accurate number is 86 billion, so slightly less. So that's a lot, you know, that's not Avogadro number a lot, but it's still a lot of neurons. And it's in particular a lot of neurons for a model like that because of this matrix of interaction. So the dynamics is really complex. However, what is interesting as well is what's the structure of this? Is it a full matrix? Is it sparse? How sparse is it? And what you have is around 6,000–7,000 synaptic connections per neuron. Right. That means the neuron, on average, right, is expected to be connected to around 6,000–7,000 other neurons in the brain, which is both large and small. Right? It's a lot. I mean, it's a lot because that means that you really don't have pairs of neurons that interact so strongly between each other, right? This is something that is much more diffused. Yes.
So this makes the graph. Is this graph oriented? I mean,
yes.
Are there synaptic connections?
Yes, it's
reversible.
No, it's not symmetric. Mm-hmm. The Wij, you cannot assume that it's symmetric in general. Yes. And so it's not only that it's oriented, because you can still have connections both ways. But then they don't necessarily have the same strength in both ways, right? So you have two oriented graphs, if you want to put it like that. Yes. So what this means is this matrix is sparse. It's really, really sparse, right? Because that is so much smaller than this.
What about the strength of the connections over that 6,000?
We have no idea.
And what is the typical diameter of the graph?
That is a very good question. And this is not something that we know for humans. So that's a little bit an interesting question from a biology point of view, right? Which is, what can we say that is more precise than that about this? And traditionally, the answer was nothing, right? And then people took a lot of models with random, some sort of random choice for the weight, because what can you do? But that creates its own set of problems, because you're introducing a big structure on the graph, depending on the randomness that you're going to pick. There has been huge progress in medical imaging, however, so that we actually have the graph, not the weight of the connection, okay? But we have the graph for some simple animals. Last year, you had a paper published with so the graph is called the connectome, in biological term. Paper was published with a connectome for a fruit fly, not an embryo, the actual fruit fly. So to give you an order of magnitude, this is 200,000-300,000 neurons, right? So a lot less, but that means several millions of connections. So this is already a huge graph if you're going to have a precise medical imaging description of it. So we might, in the near future, we might have some more precise information about what that looks like.
Is there also a worm? Like I think there's a very simple worm.
Yeah. So the fruit fly is the largest one that I know of, right? We had worms that several years ago now, and embryo fruit flies that are like a tenth of that were also done before. So this is progressing fast. And again, I'm not saying that we can get any medical imaging of Alex's brain in the near future, unfortunately, right? But we might, again, start having an idea of what is the structure of these things.
The connections are also related to electrochemistry, and they
Yes.
change.
Yes.
So
yes.
So
that was going to be my next point. There's another big issue in the model as I presented it, which is that I'm freezing the connections. And of course, they should depend on time. And there's a very famous Ebb rule in biology, which says that neurons that fire together increase their strength of connection. And that's what is supposed to cause the learning in the brain, which is super important, right? And I'm not going to take this into account. It's a difficult modeling question, how to do that in that setting, meaning for a sparse matrix, right? If a matrix is large, there are plenty of models with learning. But for a sparse matrix, if you want to do learning, you have to find a good way that you can create connections where none existed, while still keeping the sparsity and still keeping reasonable weight between the connections. So what I'm going to get out of that are the two following assumptions. And those are going to be the only assumptions that I will allow myself to make on the matrix Wij throughout the talk. And I'm going to call that the mean field scaling. You'll see why. And so what I'm going to assume is the following. The total strength, so if I pick a neuron, any neuron, right? And I calculate the sum of all the connection weights, so that's the degree of a graph. This is of order 1.
This is the L infinity norm of the matrix.
Yes. And for technical reasons, because the W is not symmetric, I'm also going to assume the other one. Right, so I'm going to assume as well that the sup over J,
This is the L1 norm.
yes, of the sum over I of Wij is both power for the one. And the next and final assumption is the maximum value of any connection is small. Now, why is this a mean field scaling? It's a mean field scaling because you see that when a neuron fires, the effect it produces on all the other neurons, right? We need to sum this over J. And so this effect is guaranteed to be of order 1. And that fixes the time scale of the firing of the neurons to be 1, which is compatible with the time scale of the dynamics I have here. Right. And the second point means that the effect of only one neuron on anything is negligible. So to see a dynamics, I will need to have several neurons acting together, and therefore I would expect that law of large number can still apply. And this fits relatively well with what we understand of a biological scaling up to now. But I insist on that this is it. I'm not allowed to assume anything else, right? I'm not allowed to assume any structure on the matrix. I don't want to presume that there's some inherent randomness one way or another. I don't want to assume that neurons that are physically close in the brain have similar connections, for example. That's essentially not true. So nothing like this.
Small compared to what?
Right. So I was hoping to postpone the answer to this question, but okay. I'll come back to this, okay? Yes.
Did you say that the firing times, are they unique or independent? Or are they
Yes, they're independent.
Okay.
The Hawkes process that I mentioned has some sort of connection between the firing time, but not here. All right. So what can I do with this? Well, there's actually a significant literature at this point about the study of non-exchangeable many-particle system. And a typical example is the following type of system. So what I've done here is I went back to a more classical type of model, right? 2x2 pairwise interactions between agents, but I put this matrix of interaction here, okay? So this is a somewhat simplified version of what I have here, but it gives a bit of an idea. And so people are asking the same questions, right? Can I write down the limit of this as n tends to infinity? And over the past 10 years, there's been now a sort of recognized strategy to do that, which is connected to the theory of graphons that some of you may know, but most probably don't. And graphons were introduced in the early 2000s, a lot by Lovash, to try to handle the large-scale limits of graphs. So I'm going to present them in the context of that, right, so that they are directly useful. And the way to do graphons here is relatively straightforward. We are going to build an interaction kernel out of that by adding an extra variable. Okay, so I'm going to define a Wn of psi zeta, where both of those variables are going to be in 0, 1, of simplicity. a compact measurable Banach space. They are all isomorphic to 0, 1 with Lebesgue, right? So why not take this one? We're just going to sum over I and j. I'm going to put wij, and then I'm going to put the indicatrix function of psi is in the interval I minus 1 over n, I over n. And j is in the interval, zeta, sorry, is in the interval, the corresponding interval, but with j. Okay, so this is very simple, right? I have a matrix. I take 0, 1 square. I cut it into pieces, small squares, right? And square, small squares. And then I enter the values of my matrix, right, in each of the square, and I built a piecewise constant function like that. Fair enough. And I can build an extended empirical measure. In a very similar way. And now the game is I'm going to write down an equation like this. It's going to involve that. And I'm going to try to pass the limit in this equation. And if you do it like that, it doesn't work. And it doesn't work because you will need some compactness on Wn, right? And Wn here is what, in some sort of L infinity L1 space, right? And that's it. And this is where graphon theory shows up, but with a stronger assumption than what I have. So I need to assume that Wn in L infinity, not L infinity L1, L infinity of both variables, right? So this norm. Behaves like one, oh, sorry. I need an n here. And now you'll see. So this is 1. Okay, so if I want things to fit well, sorry, I messed up. In an equation for that, it's not the Wn I had written that show up. It's the Wn with an n wij. And the issue is when I'm summing, right? Well, I don't have a 1 over n here. However, you see that when I'm integrating this, right, in zeta, for example, I have automatically a 1 over n that is showing up. So the correct scale of the graphon is n wij. And if that, right, so I can see it as a kernel. It's a function of 2 variables. If that in L infinity is less than 1, then there's a miracle. And the miracle is after reindexing the neurons, right? Remember at the beginning I said just pick any numbers for the neurons. Now that has become very silly. Because now I'm putting an order, right? Because psi and zeta, they are order, right? So why should 2 neurons be next to each other in the matrix, right? There was no rule for that. And so that creates a nonsense. But there is a way to pick them in the right order so that you get compactness. Wn is compact, not in an LP space, but close enough, seen as an operator from L infinity to L1, which is still a strong norm. It's not as strong as an LP norm, but it's still a strong norm. And again, it's a kernel, so it makes sense that we would have compactness of it seen as an operator norm. Now, this operator norm is connected. It's actually equivalent to what is known as the cut distance for graphons. And with this, it works. And you have a limit. And I'm not going to write the limit there because I'm interested in that. So this has not been done for integrate and fire, but you can take the existing theory and you can look at it and you can work it out. And you get the limit. So that gives us a first result. Okay. So what do I need? I need the Wij to be uniformly of order 1 over n. So I need a full matrix, one way or another. That's what we're saying here.
One question.
Yes.
The reordering, it applies both to the indexes I and j the same way.
Yeah.
Okay.
Yeah, you do a permutation, right? There is a permutation of index. And now if you apply the definition to the new, yes, yes. Another way of saying that, Jan, will like this one, right? You can instead reformulate everything in terms of measure preserving transform. Mm-hmm. And so what you're saying here is if you have a function of 2 variables that is in L infinity, there exists a measure preserving transform that if you apply it the same to both variables, then the new object is compact as an operator. Yes.
So the permutation symmetry group on your discrete system is somehow being transmitted here to this mean field.
Yes. But again, remember, one way, a biological way of saying this is there is a way to classify the neurons. And to classify the neurons by assigning numbers to neurons that have somewhat similar behavior. And if you use this classification, then you have a matrix Wij that now starts making sense. And you can pass to the mean field limit.
You do not assume positive entries, do you?
No. No. So what does the limit look like?
Define this norm as an infimum over the group of permutations.
No, it's more complicated than this because it's not a question of norm, it's a question of compactness. But you have explicit rate. I don't want to go too much in graphon theory because then I will not have the time to talk about anything else. You actually have explicit rates for compactness.
Can I also ask a question? So the way, sorry, the way I understand it is there's a permutation depending on n.
Yes.
That
Yes.
in the limit of. So the question that I ask is, are this sequence of permutations having a limit?
No, and I don't see why. In general, right? So the measure preserving function, right? If I go to that, because then it's easier to talk about the limit. So I have a sequence of measure preserving transform, and it might oscillate in a crazy manner, right?
Right. Bigger mystery.
But there's worse to come. So keep some of the good energy for what's coming in 10 minutes. Okay. So what does the limit look like? What I'm saying is there exists a W infinity, which is in L infinity of psi and zeta. And there exists an initial condition, which I'm going to talk F0 of x phi. And let me be vague about the space where this is, okay? It's not very complicated. It's just I didn't mention anything about moments at infinity, and I don't want to. And then I can solve a sort of kinetic equation where psi plays the role of the velocity that doesn't change, right? So it's a sort of free transport kinetic equation. But still nonlinear. So V, potential. W infinity of phi zeta, F of V star zeta d zeta dV star, right? So that's the interaction term times F equals Laplacian V of F. Sorry, that's the one I said I wouldn't be writing. So that's the mean field limit for that. And now I'm going to write down the mean field limit for this. And it's very, very similar, except I need to be a bit more careful. It's something like that. I have B of V plus a jump term that is going to show up also at another point. So this is the integral of W phi zeta G of zeta d zeta F. I have that. I have to subtract the things that are jumping, so it's minus nu F. And because I didn't put boundary condition, I need to add the Dirac mass at the right-hand side for the result of the jump so that they come with a zero potential. And this is just delta V equals 0 times this G of psi. And J of psi is the rate of jump, as you imagine what it is. So J of T psi is the integral of mu V F V phi. So I have a deterministic object, right? Because I have many jumps and now they all average out together. Yeah, so this is if I'm applying Graphol's theory to that model, to integrate and fire, this is what you get as a mean field limit. V is the membrane potential. Right. So it's a nonlinear equation. Right. And you see that psi plays a little bit the role of velocity because in a kinetic equation, right? Because you integrate here in the other velocity to determine what is going on, right? Yes.
What's the structure of this nu of V in the last integral?
Oh, so nu of V is just the firing rate. So here, this is just essentially how much neuron.
The structure of that function, this nu of V.
It's typically an increasing function, but you want to keep bounded to avoid problems.
Don't you need a condition that the integral of f stay equal to 1? Because otherwise, if you put j equals 0, already a family solution.
So,
but there are two terms which compensate
yes.
each other, and the integrals with respect to v is 0.
Yes.
Yeah, but if you don't put this constraint, put j equal to 0, then you have a solution.
Yes, but the j comes from Vier's. This is a nonlinear equation, right? So I just can't take it away, right?
So when you say that this is the limit, it is that you introduce also a measure, empirical measure.
Yes.
F is the limit of the empirical measure.
So F is the limit of the mu n that I introduced here, for example, right? So mu n converges weak, the usual weak star of measure.
Are there any constraints on W infinity beyond?
No. So that is relatively well understood. And that's the easy part of my talk. And now comes the mess. The mess comes from the fact that I don't have this assumption, right? We are actually, let me cover this for a minute. We are actually very, very far from it because this assumption, again, would force me to, well, ignore this number and say that this is like comparable to 10 to the 11 as well. But you know, even in Alex's brain, it's probably not true, right? Not that many synaptic connections. Maybe we can add a 0, not more than that, right? So what do we do? And that has been a topic of intense study. And you see a little bit the strategy here, right? The strategy is, well, I'm going to find a good functional setup for my graphome, Wn, right? So that I can get compactness in that functional setup, given my scaling. Then I will get, after a reindexing, I will get some things that converge. And then I will look at the limit here. And there have been a lot of attempts at doing this for sparse matrices, right? I will only cite among one of the recent ones. There's a series of papers by Godkas, Kuhn, and Shu that are trying to do this using what is called GraphUp. And GraphUp fits with that scaling, but they need some extra assumptions in those papers. And basically, they need some sort of pre-given regularity of the matrix for the process to work. And the hard truth is I have no idea how to extend this strategy to that scaling. So instead, I'm going to do something completely different and a lot messier. In the sense that I will have to give up following the trajectory of individual neurons in Alex's brain. And now I'm going to say we are just going to look at some statistical distribution at a larger scale. And then we can do something. So let me use the... And I will erase that as well. Okay, so clean start. And let's move in another direction. So statistical distribution, what do we know, right? Well, the one thing I know from exchangeable system is you look at the marginals. Okay, so I can define the marginals. The problem is the system is not exchangeable. So now I don't have one marginal of order k, right? If you pick up k particles, you have a different marginal depending on which k particles you're picking. So I have objects, right, that I am forced to denote like I1, Ik, which depends on k variables, right? And this is the joint law of VI1, VIK. And they are all different. So that's not going to be super useful, right? As you can imagine. But here I'm going to be clever. And I'm going to build a new family of observables. And I'm going to think in those terms, right? Let's say that I start with a certain particle. Okay, Let's say that I pick I1, right? Anyone you want. Okay, and I1 interacts with a lot. Let's pick just a few among which, right? So maybe I pick 2. 2 and I3. My choice, okay? I decide that I'm looking at this subset of interactions. And I can continue, right? Maybe I2, okay, but I stop here. But I3, I wanted to interact with I4, and I4, you know, I wanted to interact with 3 others, right? And at one point, I'm stopping. This gives me a graph, right? It's a tree, actually, more precisely than a graph.
You don't let I3 come back to I1.
Yes. Because, you know, I'm just looking at one possible subset of all the possible subsets of interactions in the system, right? And you can pick any which number, well, less than n, obviously, and then you can build any which tree that you want, and then you can assign indices to each node of the tree, and you have a possible subset of interactions. So we are going to build our observables on those trees.
This is a directed graph, though, yeah?
This is a directed graph, and I'm going to make a few definitions here so that you know, we understand the formula that I'm going to write. So the absolute value of tree is just going to be the total number of nodes in the tree. Okay. And I'm going to list the edges of the tree, right? So those are pairs. And I'm going to list, so I have KL in the edge of T, right? And I'm going to list them in a unique way so that to each node, I'm assigning a number, right? K. And the edge are always like this. Right? So K is upper in the tree than L. And then I'm going to denote an observable, which would depend on as many variables as I have nodes in the tree. This is like that. Okay. So I'm going to sum of our all possible choices, assigning any which index to any which node of the tree, right? So I1, I'm going to sum it over 1 to n, and then I2, I'm going to pick again from 1 to n, and then all of that, right? And I'm going to average the corresponding marginals. And I'm going to average them with a weight. That depends on the tree, and that depends on the choice of indices. And what am I going to take as a weight? Well, I'm going to take the product of all the connection weights of a tree. So I'm going to take the product over all KL in an edge, right? And once I have assigned particles to each of the node of the tree, right? So once I've picked up the I1, IT, I know which particle is on which node. So for example, here, I'm going to assign the corresponding weight to that edge, which is very logically WI1, I3. This is going to be my observables. Yes.
So just quickly, that product statement you made is the statistical independence assumption about the network.
Yes and no. I mean, it's connected to the statistical independence in the jump. That's why it's working here. But then my network is not necessarily independent, right? In the sense that I actually have correlations in all of those things. So it's a bit more messy than that. This is my choice, okay? And at this point, you might say, okay, fair enough, do what you want, right? What do I care? Because I could make another choice, right? And then what's the point in all of this? Now, you'll notice that the first one here, when I take the tree, which is just one node, right? This is the one particle distribution. So at least the first one has a natural interpretation. Right? This is 1 over n, the sum over I of fi of v. I'm taking all the marginals of order 1 and I'm averaging them. So this is the expectation of my empirical measure. But at least if I know something about the first one, I know something about the expectation of the empirical measure. I could do things that are more complicated here in the following sense. If you give me another quantity that is nice and symmetric and that you care about, I can build a second family of observables based on this quantity. And I can also give you the limit of the quantity you care about. So this is not limited to this. We can actually build such a family for everything that you want to see the limit of. But I'll stick to one, right? If you don't mind during the talk. But what's the miracle here? The miracle is those objects are almost solution to a nice hierarchy. What does it look like? Well, they are the simple terms, right? That comes just for the SDE that are independent on each neuron. So those are okay. We understand how they work. So for example, this is the advection, right? Okay. So for each node, right? So I'm summing for all the nodes of the tree, and then I'm advecting the value at each node with the corresponding advection speed, which is B of VI, right? If it's node number I. And of course, I also have, you know, the Laplacian. Right? So Laplace sum over I of Laplacian VI of tau n t. And yeah, minus sum over I of nu VI of tau n t, right? This is what happens when they fire. And now we have to write down the interaction terms, which is the interesting part in all of this. And the interaction terms, they look very much like what you would expect of a hierarchy, meaning they will involve an observables with one more order. So here I will say, yes, okay, so I have an observable with one more order, corresponds to another neuron that fired, and then that pushed the rate in the current neuron. And it's a very simple expression. Which gives something like this. Now, what is T plus I? T plus I is the tree you get by adding a leaf to the node I on the tree T. All right, so I have a tree, I have numbered the nodes. I'm looking at the evolution of node number I. I'm going to say the evolution of node number I depends on all the other particles. So they are not there in general, right? Because I've only picked a few of them. So most of the other particles are not in my list. So I'm going to need to take into account the effect of the other particles on my node I. So what do I do? Well, I need a bigger tree. I need a bigger tree with one additional connection.
Where?
On node I. So if I have a tree like this, right, and this is node number I, then what is the tree T plus I? Only there are colors, yes. It's this one. That's tree T plus I.
The sum is in I.
Yes.
Why the sum is
Yes.
over
Yes. Yes.
nodes.
Yes. Then you have the Dirac mass. Okay, I'm not going to write it down. And unfortunately, this is incorrect. Okay, life would be very, very nice. But there is no hope that starting from a joint process that is random, I would get a nice closed equation like this. Okay, so there are remainders. And the remainders are formally vanishing. Okay, this is an extension of the BBGKY hierarchy. It's a direct extension of the BBGKY hierarchy, right? If now I'm assuming that all my weights are 1 over n, all my marginals are symmetric, then this is just the marginal, right? And this is the standard BBGKY. Why do I care about that object? I care a lot about that object for the following reason. If you forget about the remainders for the time being, this does not involve at all the connection weights. This is not a mistake. This is not a typo. There is no connection weights here. That's where you see that I was actually clever in the definition of my observables. Right? That's why this formula makes sense.
I didn't understand the role of the second line here. Yeah.
So this is a weight, right?
Yes.
I have to weight the marginals. And I decide to weight them by assigning to each tree, once you picked up the indices, the specific weight. And how do I choose that? I just do the multiplication of all the connection weights on the tree.
Okay.
Right. Another way of seeing this is a subgraph of the original graph of interaction, right? So I'm looking only at the subgraphs that are trees, and then I'm averaging over all possible choice of a subgraph of a certain shape, right? So I have my tree, I'm moving it in the original graph. And then everywhere it fits, right, I assign a weight, which depends on the product of the weights.
But the cleverness is in the weight.
Yeah, the cleverness is all here.
So when you try to do an arbitrary weight and you insist
You fail.
to the limit, you discover you're clever.
Yes, yes, yes. And those objects are not positive, right? They don't have a sign. They are not probability densities or anything like that. They are not connected. So this is not really a hierarchy in the sense that the higher object, if you integrate them, do not give you the lower order objects. They are all different. But this is what I call a master equation. Because now this offers a different strategy to actually approach the problem.
So there is no reordering.
And not here. But we'll come to the reordering in 5 minutes. Okay. All right. So let's try to erase that. I should.
I'm sorry, Pierre-Emmanuel, but I don't understand where you use the weight. I understood how you constructed the marginals, but I don't understand where you use the weight. I understood the way you constructed, but I didn't understand.
So you understand why, or you understand what this is?
where do you use the way you said?
This is the sum times this, right?
Times this.
So every marginal is multiplied by that.
This is second. Okay, now I got it.
Right? So this is inside. Okay, this is inside the sum.
This is one formula. Okay. Now, now I understand. Thank you.
Right? Makes sense?
Yeah.
So every marginal has a different weight.
It's completely clear.
All right. So let me now explain the general strategy, and then I'll stop there. So how do we get to a limit? I forgot to, sorry. It's been a while, so I lost the good habits of. Okay. The first and the key point is that we need well-posedness and stability in this hierarchy of equation. What do I mean by stability? What I want to do is I don't have an exact solution. I want to pass to the limit, and if possible, I would like to obtain convergence rates. Now I can come back to your question about what does the less than one means. You have two types of results that you can write down. I'm not going to try, but you have two types. You can have a purely convergence result, saying as n tends to infinity, then this goes to a certain limit. And then what I mean by less than one is it goes to zero. But you also have quantitative result, which is to say now I'm going to take a solution to this without the remainder terms, and I'm going to compare the two. And then if you compare the two, you can show that the size of the remainder term depends directly on this maximum of the Wij. Now this looks crazy, right? Because how are you going to do well-posedness even in a BBGKY hierarchy, right? That has been a major issue for a very, very long time. Well, it turns out that we found out this is super simple. And I won't have the time to explain this. We use that to derive the Vlasov-Poisson, the mean field limit for Vlasov-Poisson-Fokker-Planck, for example, a year ago. And the reason this is simple is there is diffusion. And so as a matter of fact, on a hierarchy like that, you can propagate LP norms. And if I had 15 more minutes, I would show it to you because this is a very, very straightforward calculation. So actually, here it's not as hard as it sounds. It's a little bit harder though, because the remainders don't go to zero in any strong norm. So you need to use the proper weak norms, and it's a bit of a mess. So technically, there's still quite a bit of work to be done here, but now we understand how to do that. And so what that does is my tau n of t, I know that they are going to converge to some tau infinity of t. And I have well-posedness. Remember that, because what's the second step? Many people will not be very satisfied if I tell you that the mean field limit is a solution to an infinite dimensional hierarchy indexed by trees. Right? People are weird like that, huh? I know. But yeah, there are people like this. Instead, what they would very much like me to say is, this is the mean field limit still. Right? So how can we do that? we just need to identify t infinity at the initial time. We just need to identify each observable at the initial time. Because then I know that the dynamics is propagated by the hierarchy. And guess what? If you have a solution to this, and I built observables on that, then it's a solution to the hierarchy. So the hierarchy contains this limit. So I only need to fit at the initial times. And this is okay if the VI at the initial times are independent, for example. Even more if they are IID. So if you allow me to take good initial conditions, right, at the initial time, then I know how to show that there exists a W infinity, which is not anymore in that space, but which is in a space like that. So it's L infinity in psi measure in zeta. And yes, there are several definitions of the space. We take it as the dual of L1 continuous. That's our definition here. Then I can make sure that the observables connected to W infinity and F0 match with the limit of the initial observables here. Then I have two solutions of the hierarchy, and I have well-posedness of the hierarchy. So the two solutions, they keep fitting at any later time. Meaning your observables they still match at any later time. In particular, T1, right? T of this tree is just f of t e psi psi. That's a much more satisfactory result, right? So now I can tell you, I can find a limiting kernel in a weird space, the limiting initial condition. I can solve a PDE, and the solution to this PDE is going to give me the limit of my one particle distribution function. But I don't have any information on any individual trajectory. That is lost. I don't have uniqueness of the limit. This is actually something that we don't have already in graphons, meaning there could be several choices of W infinity and F0 that works. Which is funny because what that means is there is a set of invariant connected to this equation that is actually non-trivial, right? That is based on the hierarchy. So that if you take two solutions with different coefficients, but they have the same observables, then they keep the same observables for all times, even though those are different equations because different kernels. And that's non-trivial. I mean, I don't know of any other way of deriving this, for example. But again, you don't have a unique limit. So there are drawbacks, right, to this. And the last one that I want to emphasize is contrary to the graphon, where I was obtaining independently the limit of the kernel and the limit of the initial data. That's not true here. So if I change the initial data, but I don't change the original Wij, I may have to change the W infinity in the limit. So that's the price to pay for this, what is actually a remarkable miracle. Because there was no reason on earth that you could be able to derive a limit here without any structural assumption on the graph, for sparse graph. So there has to be consequences for this, right? And the consequences, what you get is a limit where everything now is intricated and mixed up. I'll stop here. Thank you, and happy 50-something birthday, right?